So I'm going to do a recap of normal distribution. So the key elements on normal distribution are hypothesis testing with the normal distribution, normal approximation to the binomial, finding unknown parameters using the standardization formula, and then just general things like finding probabilities or using the inverse to find areas, things like that. So the top three things, 1, 2, 3, these will basically definitely come up in every A-level stats paper. So these are the things, and they're worth quite a few marks, should be really clear with. Ultimately, they're quite similar processes every time. So we'll start off with the most common one, the most important one perhaps, which is hypothesis testing with the normal. So here's just an example of some questions. Now you definitely get a normal hypothesis test in your final exam, and they won't always necessarily be right at the start. Or like here you can see question 5D, carry out a suitable test. That was our normal hypothesis test. Question 10 here, carry out a significance level test. Carry out a hypothesis test there. There's another one down here, and this one over here, part C, that's where it is. So even if you get stuck, quite often part A and B on these sorts of questions can be quite difficult, but look for that hypothesis test question because they're always the same method. So if you learn the method well, you should be able to gain the marks. So let's talk about that method now. So the first thing to do is to state the thing that you are measuring. So X is the length of a nail. Then state the distribution. There are marks for this. With them normally distributed, as it says, with a mean of 10 and a standard deviation of 0.08, we write in the parameter as the variance, so we need to square it. Then write the hypotheses. Mu is 10, and then we're going to go on to the alternative. Now, an important element of any normal hypothesis test is you ignore the result of the test. So find that their mean length is 9.98. So this line here, so she takes a random sample of 50 and finds their mean length. This is the result of the test. Ignore this until the end. You ignore the result of the test until the end. So all your setup must be done pretending that you don't know that result. So you choose the alternative not based on that, because you're ignoring that, but based on the words. So whether the mean length of nails produced has changed. Not increased or decreased, but changed. So that means we're going to do a two-tail test. So we're going to see if it's not 10. So two-tail at 5%. Now, whenever you're doing a normal test, you're never just testing the length of one nail. That wouldn't really be that representative. We're always taking a sample and measuring the mean of that sample. So we're always doing a sample mean distribution, and that is denoted X bar. I like to write X bar 50 to remind me the size of the sample that I'm taking. And X bar 50 or X bar, whatever your sample size, will always be normally distributed if your original one is normally distributed. And it will have the same mean, but it will have a smaller variance. Now, hopefully you have some appreciation of why it might be smaller, but for now, I'm just going to tell you that you need to divide the variance by the sample size. So that's a fact you need to remember. So the fact is that if X is normally distributed with a mean of mu and a variance of sigma squared, then X bar n, the mean from a sample of size n, is also normally distributed with the same mean, but a smaller variance. That's a fact you need to remember. Now, there are two methods from this point onwards, the critical region method or the probability method. If you only knew one, you would need to know the critical region method because you're more likely to be asked to find the critical region. And the way I show my working, I find that people don't really know what working to show for this, is to draw the curve, label your mean of 10, we're still ignoring the result of the test, and then to find your critical regions. So this is a two-tail 5%. So I want the lower tail to be 2.5% and the upper tail to be 2.5%. Don't need to write any working out really now. I'm just going to use my calculator, inverse normal with 0.025, a mean of 10 and a standard deviation of the square root of 0.8 squared over 50. When you type that in, think about using brackets. And then that gives you this value here. So if you do an inverse normal, as I said, You should get 9.978 and you should get 10.02. So that means that the critical region is x bar less than 9.978 or x bar greater than 10.02. Note that I've written the critical region in terms of x bar, not x, and that's because it is in terms of x bar. We're interested to know if x bar is less than 9.978, not if a single nail is less than 9.978. It wouldn't be particularly unusual to get a single nail that was shorter than 9.978. What would be unusual is to get 50 of them which had an average that was as low as 9.978. So now we've done our critical region, we've done most of the work, we've actually gained most of our marks. We now look at the result of the test and we say 9.98. Now in fact in this case it's only slightly out of the critical region. It's greater than 9.978, only just, so is not in the critical region. And the first thing we say now is we make the conclusion in mathematical terms. So just like you're talking to another mathematician, you just say, do not reject H0. So that's just like you're talking to another mathematician. But then you have to make the public service announcement and you say, there is or is not, in this case is not, significant or sufficient, it doesn't matter. So there is not sufficient evidence to suggest, this bit's really important, and then the next bit you quote it from the question. So going back to the question, there is not significant evidence to suggest that the mean length of nails produced by the machine has changed. You quote it from the question. And that's how to do the hypothesis test using the critical region method. The alternative way of doing it is the probability method. And I'm still going to draw a diagram of the curve to represent this method. So here is 10. I'm still dealing with all the same original bits. I'm still dealing with x bar 50. And effectively, when I'm doing the probability method, I'm trying to find where the 9.98, I'm trying to find where the result of my test goes. So it's somewhere here. And what I want to know is the area up to that point bigger or less than my significance level at that tail? So, because it's 2 tail, 5%, I'm comparing it to 2.5%. So what I'm going to do is I'm going to find this area and I'm going to compare it to 2.5%. So I'm going to do on my calculator the probability that x bar 50 is less or less than or equal to, it doesn't matter on a continuous distribution. Probability that x bar 50 is less than 9.98. So I'm going to use that doing a normal CD. And I'm going to find that it's only just above 0.25%. I don't actually have the number, but I think it's something like this, roughly, let's say, which is greater than 0.025. Therefore, do not reject H0. This value we get is called the p-value of the test. So that way, possibly a little bit quicker, but the critical region method is the most important method to know. Let's have a look at this question over here. The first thing I do is I state what I'm measuring. So you might want to pause the video and have a go. So x is time of journey to school. And that's where we're going. Oh, to work, in fact. And x is normally distributed mean of 26 and a standard deviation of 4.5, so a variance of 4.5 squared. Our null and alternative hypothesis. We don't look at the result, so this thing here we pretend we don't know for a minute while we're setting up. Mu is 26, that's the current belief, and we want to see if it's decreased, so we want to see if mu is less than 26. We don't use the result of the test to determine that. It's one tail at 10%. So I'm going to state my x bar distribution. It's an average from 12 days. and that is normally distributed 26 4.5 squared over 12. I'm going to draw my distribution with a mean of 26, and it's a one-tailed lower end because I'm trying to see if it's decreased. I want that to be 0.1%. So I'm going to do an inverse normal with an area of 0.1. Parameters are these, because we're interested in x bar 12, the average from 12, not just one journey to work. And we find that this is 24.8. So the critical region is x bar 12 is less than 24.8. 23.8 is less than 24.8, so 23.8 is in the critical region. So now we conclude to other mathematicians, which is to say, reject 80. And then we write the same thing we always write, give or take one or two words. There is or is not, in this case is, significant evidence to suggest, and then we copy the wording from the question, to suggest the mean journey time has decreased. That goes in there. So that's hypothesis testing. They're pretty much all the same. Sometimes you might be asked to do it in a certain order. Sometimes you might just be asked to find the critical region. Then you might get a part B that says, what can you conclude from this? But ultimately, they're really all the same. You even don't really need to worry too much about how the question splits it up. You can pretty much do it all and then label it afterwards. Okay, so that is technique 1, hypothesis testing with a normal distribution. Okay, let's have a look at this example. I take 20 shots at goal with a 40% chance of scoring. Find the probability I score at least 10 goals. Okay, so I'm counting the number of goals I score. So x equals number of goals. Now I can only score whole numbers of goals, so it must be discrete, and it seems like a binomial distribution. 20 shots and a 40% chance of success. So it's a binomial distribution. I'm looking for the probability of scoring at least, so greater than or equal to 10. And the way I do this, on my calculator I can't look up greater than or equal to, I can only look up less than or equal to's. So if I want to know greater than or equal to 10, I'm going to look up the opposite ones. So that would be less than or equal to 9. And the two scenarios, their probability should add up to 1. So probability that x is greater than or equal to 10 is 1 minus the probability that x is less than or equal to 9, because in a discrete distribution there is no such thing as 9.3 goals. And I looked this up on my calculator and I find the final answer to be 0.8403. That's a binomial distribution. I used my calculator to do a binomial CD. Why would I do anything else? There was no need to do anything else. It wouldn't really be justified to do any sort of approximating. In the next question though, it says using a suitable approximation. So straight away I'm thinking, what approximations do I know about probability? I only know one, and that is a normal approximation to a binomial. Well, if you're not a further mathematician, you only know one. If you are a further mathematician, you have to remember that in a single maths exam, you're only required to know one. So x is the number of goals again. X follows a binomial. This time it's 200, 0.4. And we're looking for the probability of scoring at least 90. Now you could work that out on your calculator using the binomial CD function, or you could work out at least less than or equal to 89. But you've been told you must use a suitable approximation. So we're going to approximate the binomial with a normal distribution. We're going to say the binomial 200 0.4 is approximately a normal, and you need to know that the mean of a binomial, the expected value, is NP. Here's N, here's P. So 200 times 0.4, that's 80. And the variance is NP1 minus P. So that's 80 times 0.4, which is 32. In fact, it's 80 times 0.6, 200 times 0.4 times 0.6, which actually gives me 48. Remember, that's the variance. It might be worth just making a note at the side in case you're liable to forget. So now we know we can use the normal distribution to work this out. However, we've got another issue. On a discrete distribution, you can only take the whole number values. So I want to know the probability of being greater than or equal to 90. So I want 90, 91, 92, 93. On a binomial, I can only take whole number values, but on a normal distribution, I can take values like 90.7, 91.3. So what value should I allocate 90.3 to? Well, 90.3 rounds to 90, so it seems to make sense to allocate all the numbers that round to 90 to the integer 90, and all the numbers that round to 91 to the integer 91. In which case, if I want to include 90, I want to include all of these. I also want to include 91, so I want to include all of these. And I want to include 92, so I want to include all of these, and so on. So if I'm working this out, I'm going to do a continuity correction, which is to say I'm going to allocate all the numbers on the number line which round to numbers that are greater than or equal to 90. So numbers that round to a number that's greater than or equal to 90 are numbers that are 89.5 and above. Because 89.5, 89.6, etc. round to 90, and then all the other numbers above that will round to either 90 or a number bigger than 90. So we now look this up on our normal CD, and we should get the value 89.5, greater than or equal to 89.5 is 0.0852. So you'll know to do this if the question states using an approximation, using a suitable approximation, using a normal approximation to a binomial. So that's technique 2. Technique 3. You start reading a question, it's about a normal distribution, and it has an unknown parameter, maybe the mean, maybe the standard deviation, maybe both. In this question, you should be thinking about the standardization formula. That's what you need to remember. Now, it is kind of quoted in the formula book, in that sense it says in the formula book, x bar minus mu over sigma divided by root n is approximately normal with a mean of 0 and a standard deviation of 1. So the formula is kind of here, but this is for x bar n. So if we're just dealing with x, well, that's kind of x bar 1. So it's the case when n is 1. Now you can look in the formula, waste your time looking it up, try and remember that, try and figure out, or you can just remember the formula. I think it's probably worth just remembering the formula for this one. Okay, so what I do now is I draw the two different distributions. So if you're trying to do one of these questions where you have to use the standardization formula, I'm going to draw the z normal. That's the one with parameters 0, 1. And the one that I'm dealing with, which is x follows a normal mu 7.2 squared. And then I'm going to put the information on. It needs to score more than 44% to pass the test and 39% pass the test. So more than 44 should have a probability of 39%. Now from that I could guess that the mean is going to be about 42, something like that, maybe 40, depends on the standard deviation, but something along those lines. It's definitely not going to be bigger than 44. Then what I'm going to do is on the standard normal, I'm going to find the value which gives me the same area above. So I'm going to find this value here. Now I can't do inverse normals with a greater than on the class whiz calculator. So instead I'm going to use this area as 0.61. So I'm going to do an inverse normal of 0.61 using these parameters. and I find that the value is 0.2793. So this value here is the corresponding value to the 44. And the way I convert between them is to use this formula. So to get from here to here, I use that formula. Z equals x minus mu over sigma. Or in other words, 0.2793 equals 44 minus mu, which is the thing I'm trying to find, divided by sigma of my x distribution, which is 7.2. And if you rearrange that, you'll find that mu is equal to 41.99, which seems reasonable. It might be the case that you have to do this when there's two unknown parameters, in which case you just repeat the process with two different conditions, this condition, and then solve simultaneously. Once you know the mu and the sigma, you can find out anything else you might be asked to find. That's technique 3. Using the standard addition formula to find an unknown mu and sigma. Now the only other sort of thing really is just to give you these questions where they combine a few different things. So the weight of an egg is normally distributed, so let's say x is weight of one egg, let's say, one egg, and x is normally distributed 80 and variance of 5 squared. X is sold in packs of 6. Here's my distribution, here's my mean of 80. I want to find the lower quartile. So that's the one where there's 25% proportion below. So I'm doing the inverse normal of area of 0.25 using the parameters given here. And I find that the lower quartile is 76.6. Part B, I'm going to change this to 85 grams because otherwise it was a bit too small, the probability. Exactly 4 eggs from a pack weigh more than 85. Okay, well, I can work out whether one egg weighs more than 85 using my normal CD and the parameters given above, and I find that that equals 0.1586. Now if I take 6 eggs and I see if each of them is greater than 85, if it is, I call it a success. So Y is number of eggs weighing more than 85. 6 eggs to try from. 6 eggs to try from, and a probability of success of 0.1586. We want to find the probability that the number of eggs weigh more than 85 is exactly 4. So I can do this using the binomial PD. And I believe the answer is 0.00672. So this is another question where they combine different distributions, binomials and normals. This is very typical. Okay, question C. The total weight of the eggs in the pack is over 500 grams. So egg 1 plus egg 2, etc. to egg 6 add up to 500. Now you don't know, you've not been taught about adding up random variables, but you do know about the average of a normal distribution. So rather than saying the total weight is 500 or over 500, you could instead say the average from 6 eggs is greater than 500 over 6. If the average is greater than 500 over 6, then the total must be greater than 500. So that's what we're going to be interested in. So we're interested in the x bar distribution. The expected will still be the same. The expected average from 6 eggs is still 80, if the average from 1 egg is 80. But the variance is now smaller, so it's now 5 squared over n, so 5 squared over 6. And I'm trying to find the probability that x bar 6 is greater than 500 over 6, which is 83.3 recurring, and we get 0.0530. And then finally, a conditional probability could be involved. It's considered large if it weighs over 9. Let's change these numbers. If it weighs over 85, and let's turn that to 90. So an egg is considered large if it weighs over 85 grams. Find the probability a large egg weighs over 90. So the probability that the egg weighs over 90, given it's large, or in other words, given that it already weighs over 85. Any question about conditional probabilities, you should be using this formula. Probability of A given B is the probability of A intersection B over the probability of B. So here I'm saying the probability of x over 90, x is greater than 90 and x is greater than 85 divided by the probability that x is greater than 85. Well, on the bottom, that's easy. We've already worked that out. So with no other conditions, what's the probability that the egg is greater than 85? We work that out in part B, and that's 0.1586. And on the top, the probability of being greater than 90 and greater than 85, well, that's just the probability of being greater than 90. And the probability of being greater than 90, I can look up by doing a normal CD, and I get 0.02275 over 0.1586, which is 0.143. So it's quite typical to have these questions where they combine different bits of the normal distribution, especially with a binomial or a conditional probability. So let's have a look at this exam question down here. What different aspects can we see? So we've got a normal distribution with a mean, and we've not got a standard deviation. So what's the sigma? Unknown parameter. We're probably going to have to use the standardization formula. Given that 15% of bottles contain less than 24.63, there's some information perhaps. Now, in fact, this question, there is a slightly different way of doing it, but that's the sort of lines you should be thinking along. Next question. A random sample of 200 is taken using a normal approximation. So we know now we're doing technique 2, I think it was, the normal approximation to the binomial. So 200 bottles, certain condition, it's a binomial, but we're going to turn it into a normal. So we know that's coming. Even if we get stuck on that, we can still carry on, and then when we look at part C, without even reading all the information, we can see we're doing a hypothesis test. So it's either going to be a normal hypothesis or a binomial one. Are we looking for the average from a sample or the number of successes from a sample? It looks like we're looking for the average from a sample. So this must be a normal hypothesis test. Okay, so that's a rundown. Obviously, questions can sometimes be a little bit trickier than that, but if you can do those key skills for those sorts of questions, even if there's a real stinker of a question in there, it's not that big a deal. If you can do all of these key areas, you're going to be picking up so many marks anyway.